There is a quality shared by nearly every object in the known universe, from the smallest detectable particles to the largest structures astronomers have ever mapped. Almost everything is turning. Planets rotate on their axes. Stars spin through their life cycles. Galaxies sweep their arms slowly through space over hundreds of millions of years. Even at scales far below what the eye can see, particles carry a property that physicists call spin, a fundamental characteristic baked into the nature of matter itself. Tonight, we are going to explore why. We will move through the universe scale by scale, beginning with the familiar rotation of our own planet and our own solar system, and expanding outward through stars, black holes, galaxies, and the large-scale structure of the cosmos. Along the way, we will look at the physics that makes rotation so persistent, so universal, and so deeply connected to the way the universe is structured. We will also turn inward briefly toward the quantum world, where spin takes on a meaning quite different from anything we experience in daily life. This is Sleepy Time Universe. We move through these ideas slowly and without urgency. Each concept will have room to settle before we move to the next. If you are listening as you drift towards sleep, you are welcome to let these ideas wash over you at whatever depth feels comfortable. There is no need to follow every detail. The universe will keep spinning whether or not you catch every word. Get comfortable. We will begin at the beginning. Not the beginning of the universe, but the beginning of understanding what rotation actually is and why physics holds it in such high regard. Chapter 1. What is rotation? To understand why everything spins, we first need to spend some time with what spinning actually means in the language of physics. Rotation is not simply an object moving in circles. It is something more precise and more fundamental than that. And the concept that sits at its heart is one of the most important in all of classical mechanics. That concept is angular momentum. When an object moves in a straight line, it carries what physicists call linear momentum, a quantity that combines the object's mass with its velocity. A heavy truck moving quickly has a great deal of linear momentum. A feather drifting slowly has very little. Linear momentum is conserved in a closed system, meaning that unless an outside force acts on the system, the total linear momentum stays the same. This is why a billiard ball continues rolling after it has been struck, and why a spacecraft moving through empty space keeps moving without any engine running. Angular momentum works in a similar way, but it describes rotation rather than straight-line motion. When an object rotates, either spinning on its own axis or orbiting around some central point, it possesses angular momentum. The quantity depends on three things: how much mass the object has, how that mass is distributed relative to the axis of rotation, and how fast it is rotating. An object with more mass distributed farther from the axis, or faster rotation, carries more angular momentum. What makes angular momentum so significant is the same property that makes linear momentum significant. It is conserved. In a closed system with no external torque, no external twisting force acting on it, the total angular momentum stays constant. It does not leak away. It does not diminish over time. Once angular momentum exists in a system, it continues to exist unless something deliberately removes it or transfers it elsewhere. This conservation law is why a spinning figure skater speeds up when they pull their arms inward. Their total angular momentum is fixed. As they draw their mass closer to the axis of rotation, the only way for the total to remain constant is for the rotation rate to increase. The physics is elegant, and it applies not just to figure skaters, but to collapsing gas clouds, forming planetary systems, and neutron stars crushed from stellar cores in catastrophic explosions. To picture angular momentum at an intuitive level, think of a spinning top. When you set it spinning on a surface, it continues to spin for a surprisingly long time. Without friction, it would spin indefinitely. The energy you put into it at the start has nowhere to go. The top resists changes to its rotation. It even resists falling over, precessing slowly around its vertical axis instead of simply tipping. This resistance to change is angular momentum in action. Now scale that image up. Replace the top with a planet. Replace the surface friction with the near vacuum of space, where almost nothing acts to slow the planet's rotation. The planet spins for the same reason the top spins, because angular momentum was put into the system at the beginning, and nothing has taken it away. This brings us to a natural question. Where did the angular momentum come from in the first place? For a spinning top, the answer is obvious. A human hand provided the initial twist. For a planet, the answer requires us to go back to the very earliest stages of planetary formation, billions of years ago, when our solar system was nothing more than a slowly swirling cloud of gas and dust drifting through the galaxy. The angular momentum of every planet in our solar system, and of the Sun itself, traces back to that original cloud. Understanding how that cloud collapsed and concentrated its rotation is one of the central stories of planetary science, and it is where we will turn next. Before we move on, it is worth pausing with one more aspect of angular momentum that will become important later in our journey. Angular momentum is not just a quantity, it is a vector. It has both a magnitude and a direction. The direction is defined by the axis around which the rotation occurs. For a planet spinning counterclockwise when viewed from above its north pole, the angular momentum vector points upward, out of the North Pole. This directionality matters enormously when we consider how rotation behaves during collisions, mergers, and the complex gravitational interactions that shape planetary systems and galaxies alike. For now, the key idea to carry forward is simple. Rotation is conserved. Once a system begins to spin, it tends to keep spinning. The universe is full of spinning objects, not because something keeps pushing them, but because nothing is stopping them. Chapter 2. The Spinning Solar Nebula. About 4.5 billion years ago, the region of space that would eventually become our solar system was occupied by a vast, diffuse cloud of gas and dust. This cloud was composed mostly of hydrogen and helium, the two lightest elements left over from the early universe, along with smaller quantities of heavier elements forged in the cores of stars that had lived and died long before our sun was born. The cloud was enormous by any human measure, stretching across a volume far larger than our entire solar system today. This cloud was not perfectly still. Nothing in the universe ever is. It had a slow, gentle rotation, barely perceptible over short time scales, but present nonetheless. The rotation arose from the same kinds of processes that give angular momentum to all large structures in the universe. Turbulence within the cloud, gravitational influences from neighboring clouds and stars, and the cumulative effects of countless small interactions over vast stretches of time all contributed small amounts of angular momentum to the cloud as a whole. None of these contributions was dramatic. Together, they added up to a net rotation, a slight tendency for the cloud to be turning in one direction rather than another. At some point, something triggered the cloud to begin collapsing under its own gravity. The trigger may have been the shock wave from a nearby supernova, a massive star that had ended its life in a catastrophic explosion sending a ripple of compressed gas outward through the surrounding space. Or the trigger may have been a chance fluctuation in the cloud's density, creating a region dense enough for gravity to begin pulling surrounding material inward. Whatever the cause, the collapse began. As the cloud collapsed, something predictable happened. The same physics that speeds up a figure skater pulling in their arms began to operate on an enormous scale. As the cloud's material fell inward, the radius of the rotating system decreased. With the total angular momentum conserved, the rotation rate had to increase. The cloud began to spin faster. This is one of the most important and beautiful consequences of angular momentum conservation in astrophysics. A slowly rotating cloud of enormous size collapses into a much smaller, faster spinning system. The rotation that was barely noticeable across the full extent of the original cloud becomes highly significant once the material has concentrated into a tighter volume. As the collapse continued, another effect took over. Material falling directly toward the center was able to reach it relatively quickly, but material that had any sideways motion, any component of velocity that was not aimed directly at the center, could not simply fall straight in. The rotation of the system gave the falling material a sideways velocity, and this sideways motion prevented it from falling all the way to the center. Instead, the material settled into a flattened, rotating disk around the growing central concentration. This disk is what astronomers call a protoplanetary disk, or sometimes a solar nebula. It is a natural and nearly inevitable consequence of angular momentum conservation during gravitational collapse. Almost any collapsing cloud with even a tiny initial rotation will form a disk. The disk is not a coincidence or a special feature of our solar system. It is what physics demands. Within this disk, the temperature and density varied from place to place. Near the center, where the protostar, the infant sun, was gathering mass and generating heat, temperatures were high. Only materials with very high melting points could exist in solid form close to the forming sun. Metals and silicates, the building blocks of rocky planets, could survive the heat near the center. Farther out, where temperatures were lower, more volatile materials, water ice, methane, ammonia, could also exist in solid form. This temperature gradient would ultimately determine what kinds of planets formed in different parts of the solar system. The disk itself was not static. Material within it was constantly in motion, colliding, clumping, and gradually accumulating into larger and larger bodies through a process called accretion. Tiny dust grains stuck together to form pebbles. Pebbles accumulated into boulders. Boulders collided and merged to form planetesimals, objects ranging from hundreds of meters to hundreds of kilometers across. And planetesimals, through continued collisions and gravitational attraction, grew into the protoplanets that would eventually become the planets we know today. Throughout this entire process, the angular momentum of the original cloud was being distributed among all the objects that formed from it. The sun, sitting at the center, accumulated the vast majority of the system's mass. The planets, moons, asteroids, and comets that formed in the disk inherited portions of the original cloud's angular momentum. It is worth noting something perhaps surprising about how angular momentum is distributed in our solar system today. The sun contains more than 99% of the solar system's mass, yet it carries only a small fraction of the system's total angular momentum. The planets, despite their relatively tiny masses, collectively carry most of the angular momentum. Jupiter alone accounts for a large portion of the solar system's total angular momentum, primarily because of its enormous mass combined with its orbital distance from the Sun. This distribution reflects the complex history of the solar nebula's evolution. The way angular momentum was transferred outward through the disk as the system formed. Understanding exactly how this happened is still an active area of research in planetary science, and models continue to be refined as new observations from telescopes and planetary missions provide additional data. What we can say with confidence is this: the solar system spins because the cloud it formed from was spinning, and that cloud was spinning because angular momentum, once present in a system, does not simply vanish. It persists, concentrates, and shapes the structures that emerge from collapse. Chapter 3. Why planets rotate. Every planet in our solar system rotates. They do not all rotate in the same direction, at the same speed, or at the same angle. Mercury completes one full rotation in approximately 59 Earth days. Jupiter, despite being by far the largest planet in the solar system, completes a full rotation in just under 10 hours. Venus rotates so slowly and in the opposite direction to most other planets that a single Venusian day is longer than a Venusian year. Uranus rotates on its side, its axis tilted so severely that its poles point almost directly toward the Sun at certain points in its orbit. This variety tells us something important. While all planets inherit their basic rotation from the solar nebula, the details of each planet's spin are shaped by a complex history of collisions, gravitational interactions, and in some cases, the ongoing influence of neighboring bodies. The solar nebula provided the raw material and the general direction of rotation. Everything else was determined by what happened during and after the formation process. To understand how individual planets acquired their spin, we need to think about what planetary formation actually looks like at the scale of individual collisions. A growing protoplanet does not accumulate mass smoothly and evenly. It grows through impacts, some small and gentle, others catastrophic. Every object that strikes the growing planet delivers not only mass, but also angular momentum. If the impacting object strikes slightly off-center, which is far more common than a perfectly head-on collision, it imparts a rotational push to the planet. Over millions of years of accretion, a planet receives countless impacts from all directions. The rotation that results is the cumulative sum of all these angular momentum contributions. If the impacts are randomly distributed, they tend to partially cancel each other out, but they rarely cancel perfectly. The residual rotation, the net angular momentum left over after all those impacts, becomes the planet's spin. This statistical process explains why planetary rotation rates vary so widely. A planet that happened to receive a series of large impacts all arriving from similar directions would end up spinning faster than one whose large impacts came from random directions and largely cancelled each other out. The details of each planet's accretion history are unique, and those details are written into the rotation rate we observe today. For the inner rocky planets, Mercury, Venus, Earth, and Mars, the situation is further complicated by subsequent events. These planets formed in a region of the solar system where conditions were relatively crowded and chaotic. Large impacts continued well after the main accretion phase ended, during a period astronomers call the Late Heavy Bombardment. This was a time, roughly 3.5 to 4 billion years ago, when the inner solar system experienced an intense period of impacts from asteroids and comets, possibly stirred up by shifts in the orbits of the giant outer planets. Earth's rotation today bears the mark of one particularly significant impact. The leading model for the formation of the Moon holds that a Mars-sized body, which planetary scientists have named Theia, struck the early Earth at a glancing angle sometime during the first 100 million years of the solar system's history. The collision was enormous by any measure. It melted a large portion of Earth's outer layers, ejected a vast amount of material into orbit, and dramatically altered Earth's rotation. The material ejected into orbit eventually coalesced into the Moon. The angular momentum delivered by Thayer's impact contributed to Earth's current rotation rate and axial tilt. Without that collision, Earth might rotate at a very different speed and at a very different angle. The 23.5-degree tilt of Earth's axis, which drives our seasons, is in part a legacy of that ancient and violent encounter. Venus presents a particularly interesting case. It rotates extremely slowly. One Venusian day lasts about 243 Earth days, and it rotates in the retrograde direction, meaning it turns opposite to the direction most planets rotate. When viewed from above the solar system's north pole, most planets rotate counterclockwise. Venus rotates clockwise. Two main hypotheses have been proposed to explain this. One is that Venus suffered a large impact at some point in its history that reversed its rotation. The other is that gravitational interactions between Venus's thick atmosphere and the Sun, combined with tidal forces, gradually slowed and eventually reversed the planet's original prograde rotation over billions of years. Current evidence suggests that tidal and atmospheric effects may be sufficient to explain Venus's unusual rotation without requiring a catastrophic impact, though the question has not been fully resolved. Uranus presents an even more dramatic case of rotational oddity. Its axial tilt is approximately 98 degrees, meaning it rotates almost on its side relative to the plane of the solar system. For part of its 84-year orbit, one pole points almost directly at the Sun, while the other faces deep space. The most widely accepted explanation is a massive impact early in the solar system's history, a collision with an Earth-sized or larger body that knocked Uranus onto its side. The evidence for this interpretation is found not only in the tilt itself, but also in the configuration of Uranus's moon system, which orbits in the same tilted plane as the planet's equator, suggesting the moons formed from debris after the impact. Mars has a rotation period remarkably similar to Earth's, about 24 hours and 37 minutes. This similarity is almost certainly a coincidence of the accretion history of the two planets, rather than any fundamental physical connection. Mars also has an axial tilt of about 25 degrees, close to Earth's. But unlike Earth, Mars lacks a large stabilizing moon. Earth's moon acts as a gravitational anchor that prevents Earth's axial tilt from wandering dramatically over long time periods. Mars, without that anchor, has experienced much more significant variations in its tilt over millions of years, which has had profound effects on its climate history. Jupiter and Saturn, the gas giants, rotate quickly. Jupiter's 10-hour day and Saturn's roughly 10.5-hour day reflect the dynamics of their formation in the outer solar system, where they accumulated vast quantities of gas rapidly. The rapid accretion of material from a rotating disk naturally produces fast-spinning planets when the accreting body is large enough to gather material from a wide area of the disk. What all of these cases illustrate is that planetary rotation is not a simple, uniform property stamped onto planets by their formation environment. It is a record, imperfect and complex, of each planet's individual history. The direction, speed, and tilt of a planet's rotation encode information about the impacts it experienced, the gravitational interactions it underwent, and the particular region of the solar nebula from which it formed. In this sense, every spinning planet is a kind of archive. The rotation we observe today is the accumulated result of billions of years of angular momentum being added, redirected, and partially cancelled through collisions and gravitational forces. The archive is not easy to read in full, but with enough observations and careful modelling, planetary scientists continue to piece together the stories these rotations tell. Chapter 4: Moons and Tidal Locking. Planetary rotation does not exist in isolation. Planets exert gravitational influence on their moons, and moons exert gravitational influence back on their planets. Over long enough timescales, these mutual gravitational tugs can dramatically alter rotation, sometimes slowing it, sometimes redirecting it, and in many cases producing a remarkable phenomenon known as tidal locking. Tidal locking occurs when the gravitational interaction between two bodies has slowed the rotation of the smaller body until it rotates exactly once for every orbit it completes around the larger body. The result is that the smaller body always presents the same face toward its companion. The Moon is the most familiar example of this. The Moon rotates once on its axis for every orbit it completes around Earth, which is why we always see the same side of the Moon from Earth's surface. The far side of the Moon, sometimes called the dark side, though that name is misleading since it receives just as much sunlight as the near side, remained completely unseen by human eyes until spacecraft first travelled around the Moon in the 20th century. The mechanism behind tidal locking is gradual but relentless. When a moon orbits a planet, the planet's gravity does not pull uniformly on every part of the Moon. The near side of the Moon, being closer to the planet, experiences a slightly stronger gravitational pull than the far side. This differential pull distorts the Moon's shape slightly, creating a tidal bulge, an elongation oriented roughly toward the planet. If the Moon is rotating at a rate different from its orbital period, this tidal bulge does not point perfectly toward the planet. The Moon's rotation carries the bulge slightly ahead of or behind the direction of the planet. The planet's gravity then pulls on this misaligned bulge, creating a torque, a rotational force, that gradually slows the Moon's rotation until the bulge aligns with the planet. At that point, the Moon's rotation rate matches its orbital period exactly, and the system is tidally locked. The same process can work in reverse. Earth's rotation is being gradually slowed by the gravitational influence of the Moon. The Moon raises tidal bulges in Earth's oceans, and to a lesser extent in Earth's solid rock. Because Earth rotates faster than the Moon orbits, these bulges are carried slightly ahead of the Moon's position. The Moon pulls back on these bulges, slowing Earth's rotation by a tiny but measurable amount, approximately 2 milliseconds per century. This energy is not lost from the system. It is transferred to the Moon, which responds by very slowly moving to a higher orbit, spiraling imperceptibly outward from Earth over geological timescales. This exchange, Earth slowing, Moon moving outward, will continue until, far in the future, Earth's rotation rate matches the Moon's orbital period. At that point, Earth and Moon will be mutually tidally locked, each always showing the same face to the other. This is already the case for Pluto and its largest moon Charon, which are mutually tidally locked and orbit each other like a slow, synchronized pair, always facing each other across the space between them. Tidal locking is extremely common in the solar system. Most of the large moons of the giant planets are tidally locked to their host planets. Io, Europa, Ganymede, and Callisto, the 4 large Galilean moons of Jupiter, are all tidally locked. The large moons of Saturn, including Titan, are tidally locked. This is not surprising given the immense gravitational influence of Jupiter and Saturn and the billions of years over which tidal forces have had time to operate. The time required to achieve tidal locking depends on several factors. Moons that are larger, closer to their host planet, and orbiting around more massive planets become tidally locked more quickly. Moons that are small, distant, or orbiting less massive planets take longer. Some moons in the outer solar system have not yet achieved full tidal locking because they formed relatively recently, or because they orbit at great distances where tidal forces are weaker. Mercury offers an interesting variation on the standard tidal locking story. For many years, astronomers believed Mercury was tidally locked to the Sun, always showing the same face toward it. Observations made in the 1960s using radar showed that this was not quite right. Mercury is in a state called a spin-orbit resonance. It completes exactly 3 rotations for every 2 orbits around the Sun. This 3-to-2 resonance is stable because of Mercury's slightly elliptical orbit and represents a different kind of gravitational relationship between rotation and orbital motion, one that is stable but different from the 1-to-1 resonance of true tidal locking. Tidal locking has profound consequences for the surfaces and interiors of the bodies involved. A tidally locked moon experiences dramatically different conditions on its near and far sides. For a moon like Europa, which orbits within Jupiter's intense magnetic field and radiation environment, the near side faces a constant bombardment that the far side is largely shielded from. For Io, the most volcanically active body in the solar system, the tidal forces from Jupiter and from the gravitational interactions with neighboring moons stretch and squeeze Io's interior continuously, generating the heat that drives its extraordinary volcanism. On Earth, the tidal influence of the moon shapes ocean patterns, influences ecosystems, and has played a role in the evolution of life over billions of years. The rhythmic rise and fall of ocean tides is a direct consequence of the same differential gravitational forces that produce tidal locking elsewhere. The connection between these large-scale gravitational phenomena and the day-to-day patterns of life on Earth's coastlines is one of the more quietly remarkable connections in planetary science. Rotation, then, is not a fixed property of a moon or planet. It evolves over time under the steady influence of gravity. What begins as a freely spinning body gradually finds its rotation shaped and constrained by its gravitational relationships with neighboring objects. Over geological and astronomical timescales, the universe tends toward synchronization, toward states where the rotations of bodies are in stable resonance with their orbital motions. Tidal locking is the most common outcome of this tendency, and the solar system is full of examples of it. Chapter 5. The Sun's Rotation. The Sun is the dominant object in our solar system by almost every measure. It contains more than 99% of the system's total mass. Its gravity governs the orbits of every planet, moon, asteroid, and comet within a vast region of space extending well beyond the outermost planets. Its light and heat drive the chemistry of planetary atmospheres and the biology of every living thing on Earth. And like everything else in the solar system, it rotates. The Sun's rotation, however, is unlike anything we encounter when we think about the rotation of solid bodies like planets. The Sun is not solid. It is an enormous sphere of plasma, a hot, electrically charged gas, and different parts of it rotate at different rates. This property is called differential rotation, and it is one of the most distinctive and consequential features of the Sun's behavior. At the Sun's equator, the surface completes one full rotation in approximately 25 days. At higher latitudes, closer to the poles, the rotation is slower. Near the poles, a full rotation takes closer to 35 days. This difference of roughly 10 days between equatorial and polar rotation rates might seem subtle, but its consequences for the Sun's magnetic field and for the activity cycle that drives solar weather are profound. To understand why the Sun rotates differentially, we need to think about the nature of plasma and how it moves under the influence of gravity, pressure, and the Sun's own rotation. In a solid body, all parts are mechanically connected. When one part rotates, all parts rotate at the same rate. The Sun has no such mechanical connection between its different regions. The plasma in the Sun's interior and atmosphere is free to move independently, responding to local forces rather than being constrained to match the rotation of neighboring regions. The Sun's interior is divided into distinct zones based on how energy moves through them. The innermost region, called the radiative zone, extends from the core out to about 70% of the Sun's radius. In this region, energy produced by nuclear fusion in the core travels outward very slowly, carried by radiation. Photons that are continuously absorbed and re-emitted by the dense plasma, gradually diffusing outward over what can amount to hundreds of thousands of years. Above the radiative zone lies the convective zone, which extends from 70% of the Sun's radius out to the visible surface. In this region, energy moves differently through convection. Hot plasma rises from below, releases energy near the surface, cools, and sinks back down. This constant churning of material, similar in some ways to the convection that occurs in a pot of heated water, dominates the outer layers of the Sun. It is the interaction between this convection and the Sun's rotation that produces differential rotation. The rising and sinking of plasma in the convective zone is influenced by the Coriolis Effect, the same phenomenon that influences large-scale weather patterns on rotating planets. Near the equator, the Coriolis Effect deflects the rising plasma in ways that carry more angular momentum to the surface, resulting in faster rotation. Near the poles, the dynamics are different, and the surface rotates more slowly. Beneath the convective zone, at the boundary between it and the radiative zone, lies a thin region called the tachocline. This layer is particularly important for the Sun's magnetic behavior. In the tachocline, the differential rotation of the convective zone meets the more uniform rotation of the radiative zone below. The shear, the difference in rotation rates across this boundary, is thought to be responsible for amplifying and organizing the Sun's magnetic field. The Sun's magnetic field is generated by the movement of electrically charged plasma. As the Sun's differential rotation stretches and twists the magnetic field lines over time, the field becomes increasingly complex and tangled. This process, which operates on an approximately 11-year cycle, drives the solar activity cycle that produces sunspots, solar flares, and coronal mass ejections. Sunspots are regions of the Sun's surface where intense, concentrated magnetic fields suppress the convective transport of energy, causing those regions to be cooler and therefore darker than their surroundings. They appear dark against the brighter solar disk, though in isolation, a sunspot would be brilliantly luminous by any earthly standard. The number of sunspots visible at any given time follows the 11-year cycle, rising from a solar minimum. When the Sun's surface is relatively calm and sunspot-free, to a solar maximum, when sunspot activity peaks and the magnetic field is at its most complex and energetic. Solar flares and coronal mass ejections, explosive releases of energy and plasma from the Sun's outer atmosphere, are also products of the magnetic complexity driven by differential rotation. When magnetic field lines in the corona become sufficiently tangled, they can undergo a sudden reconfiguration called magnetic reconnection, releasing enormous amounts of energy in a short time. The resulting burst of radiation and charged particles can travel across the solar system, and when directed toward Earth, can interact with our planet's magnetic field and upper atmosphere in ways that produce auroras and, in extreme cases, disrupt satellite communications and power grids. The Sun's rotation also drives a continuous outflow of plasma called the solar wind. Charged particles, primarily protons and electrons, stream outward from the Sun's corona in all directions at speeds of several hundred kilometers per second. Because the Sun is rotating, this outflow does not travel in straight lines from the Sun's perspective. It curves into a spiral pattern, following what is called the Parker spiral after the physicist Eugene Parker, who first described it mathematically in the 1950s. The solar wind fills the entire inner solar system, shaping the magnetic environments of all the planets and driving the plasma tails of comets to point always away from the Sun, regardless of the direction of the comet's travel. The Sun will continue to rotate for billions of years to come, though its rotation rate will gradually change as it ages and evolves. Stars tend to slow their rotation over time as the solar wind carries angular momentum away from the star. This magnetic braking, as it is called, is a significant factor in the rotational evolution of stars across their lifetimes, a topic we will explore in more depth in the next chapter, when we turn from our own star to the broader population of stars throughout the galaxy. For now, the Sun offers us a vivid illustration of something important. Even in a single object, rotation is not simple. The Sun rotates, but it rotates in a layered, complex way that depends on its internal structure and composition. That complexity drives the magnetic behavior that in turn shapes the environment of the entire solar system. Rotation, at the scale of a star, is not merely a descriptive fact. It is a mechanism, one of the primary engines of a star's activity and influence. Chapter 6. Spinning Stars. Beyond our own Sun, the universe contains an almost incomprehensible number of stars. Current estimates suggest that the observable universe holds somewhere in the range of 200 billion trillion stars, a number so large it resists any meaningful visualization. Every one of these stars rotates, and across that vast population, the variation in rotation rates is extraordinary. Some stars rotate slowly, completing a single rotation in weeks or even months. Others spin at tremendous speeds, rotating in a matter of hours. The rotation rate of a star is not fixed at birth. It changes throughout the star's life, shaped by the processes of formation, magnetic activity, mass loss, and in some cases dramatic interactions with companion stars or with the remnants of stellar death. Stars form from the same basic process we described for the Sun, the gravitational collapse of a rotating cloud of gas and dust. As the cloud collapses, angular momentum is conserved, and the young star, called a protostar during its formation phase, spins faster as it contracts. At this early stage, protostars tend to rotate quite rapidly, but as they settle into their main sequence lives, the long, stable period during which they fuse hydrogen into helium in their cores, several mechanisms work to slow their rotation. The most important of these mechanisms is magnetic braking. Young stars possess strong magnetic fields that interact with the surrounding disk of gas and dust from which they formed. The magnetic field lines, anchored to the rotating star, extend outward into the disk. As the disk material orbits the star at a rate different from the star's rotation, the magnetic field lines create a coupling between the star and the disk that transfers angular momentum outward. the star slows down. The disk material gains angular momentum and moves to wider orbits. This process, called disk locking or magnetic braking, can significantly reduce the rotation rate of a young star during the first few million years of its life. Once the disk dissipates, blown away by the star's radiation and stellar wind, the magnetic braking mechanism changes character, but does not stop entirely. The stellar wind that flows outward from the star's surface carries charged particles along magnetic field lines. As these particles move outward and eventually escape the star's magnetic field, they carry angular momentum with them. The result is a slow but continuous drain on the star's rotation over billions of years. This is why older stars, like our middle-aged sun, tend to rotate more slowly than their younger counterparts. Astronomers have used this relationship between stellar age and rotation rate as a tool for estimating stellar ages, a technique called gyrochronology. Because the rate at which a star's rotation slows is fairly predictable and depends primarily on the star's mass, measuring a star's rotation period can provide a reasonable estimate of its age. For stars similar to the Sun, this technique can place useful constraints on stellar ages that complement other methods based on stellar brightness, temperature, and chemical composition. The mass of a star plays a central role in determining how quickly it rotates. Massive, hot, luminous stars, the O and B type stars that blaze blue-white and burn through their hydrogen fuel in millions rather than billions of years, tend to rotate very rapidly. Some of the most massive stars known rotate at speeds approaching a significant fraction of the velocity at which they would fly apart. Their equatorial rotation speeds can exceed 300 kilometers per second. At these extreme rotation rates, the stars are noticeably flattened at the poles and bulging at the equator, their shapes distorted by the centrifugal effects of their rapid spin. These rapid rotators are not merely an astronomical curiosity. Fast rotation has significant consequences for the internal structure and evolution of massive stars. Rapid rotation drives mixing between the stellar core and the outer layers, bringing freshly synthesized elements up from the core and mixing hydrogen-rich material down toward the fusion region. This mixing extends the star's hydrogen-burning lifetime and alters the chemical composition of its outer layers. Some categories of chemically peculiar stars, stars with unusual abundances of certain elements in their atmospheres, owe their peculiarities in part to the mixing driven by rapid rotation. For lower mass stars like the Sun, rotation rates are more sedate but still significant. Sun-like stars in young star clusters rotate with periods ranging from a day or two up to several weeks. Over billions of years of magnetic braking, these rotation rates converge towards slower, more uniform values. By the time a Sun-like star is several billion years old, its rotation period has typically settled into a range of weeks to months, and the spread in rotation rates among stars of similar age and mass becomes much narrower. Red dwarf stars, the smallest, coolest, and most common type of star in the galaxy, present a particularly interesting picture of stellar rotation. Young red dwarfs can rotate rapidly, with some completing a full rotation in less than a day. As they age, magnetic braking slows their rotation, but the process operates differently for red dwarfs than for Sun-like stars. Red dwarfs are fully convective. Unlike the Sun, which has a distinct radiative zone and a tachocline, red dwarfs have convection operating throughout their entire interiors. This affects the structure of their magnetic fields and the efficiency of magnetic braking in ways that astronomers are still working to fully understand. Some red dwarfs that are billions of years old still rotate surprisingly quickly, while others of similar age have slowed considerably. The reasons for this diversity are not fully resolved, and active research continues into the rotational evolution of low-mass stars and the factors that govern how efficiently they shed angular momentum over time. Binary star systems, systems where two stars orbit each other, add another layer of complexity to stellar rotation. In close binary systems, tidal forces between the two stars act much like the tidal forces between a planet and its moon, gradually synchronizing the star's rotation with their orbital period. Close binaries can become tidally locked, with each star always presenting the same face to its companion. The transfer of angular momentum in close binary systems also plays a role in some of the most dramatic phenomena in stellar astronomy, including the formation of certain types of novae and supernovae. Explosive events that arise when one star in a binary system transfers mass to its companion in ways that push the receiving star past critical thresholds. The story of stellar rotation is ultimately a story about angular momentum flowing through systems over vast stretches of time. Stars are born spinning, and they carry that spin throughout their lives, shaped and slowed by the continuous processes of magnetic activity and mass loss. When stars die, their rotation, or what remains of it, is carried forward into whatever comes next. For some stars, that means a white dwarf cooling quietly over billions of years. For others, it means something far more extreme, as we will explore in the chapters ahead. Chapter 7. Pulsars, rotation at its extreme. When a massive star reaches the end of its life, the sequence of events that follows is among the most violent in the universe. The star has spent millions of years fusing progressively heavier elements in its core, working through hydrogen, helium, carbon, neon, oxygen, and silicon in a series of increasingly rapid fusion stages. When the core finally fills with iron, an element that cannot release energy through fusion but only absorb it, the core becomes unable to support the weight of the star above it. In a fraction of a second, the core collapses catastrophically. What happens next depends on the mass of the collapsing core. If the core mass falls within a certain range, the collapse is halted by a quantum mechanical effect called neutron degeneracy pressure. The protons and electrons in the core are crushed together to form neutrons, and the resulting object, a neutron star, is stabilized against further collapse by the resistance of neutrons to being packed any more tightly together. The outer layers of the original star, falling inward at tremendous speed, rebound off this newly formed neutron star in a shockwave that tears the star apart in a supernova explosion, visible across billions of light years. What remains at the center of the explosion is a neutron star, an object typically containing between 1 and 2 times the mass of the Sun, compressed into a sphere perhaps 20 kilometers across. To put that scale in perspective, a neutron star of 1 solar mass squeezed into a sphere the size of a city would have a density so extreme that a single teaspoon of its material would weigh billions of tons on the Earth's surface. Gravity at the surface of a neutron star is approximately 200 billion times stronger than gravity at Earth's surface. And neutron stars spin. They spin extraordinarily fast. The reason, again, comes down to angular momentum conservation. The original stellar core, before collapse, was rotating. Slowly, as massive stellar cores go, but rotating nonetheless. As the core collapsed from an object perhaps the size of Earth to an object 20 kilometers across, the same physics that spins up a figure skater pulling in their arms operated on a dramatic scale. The rotation rate increased enormously. A core that was rotating once every few hours before collapse might emerge from the collapse rotating many times per second. Newly formed neutron stars have been observed rotating at rates ranging from a few times per second up to hundreds of times per second. The fastest known neutron stars, called millisecond pulsars, complete more than 700 full rotations every second. To appreciate how remarkable this is, consider that the entire object, containing more mass than the Sun, packed into a sphere 20 kilometers across, is completing over 700 full rotations per second. Its equator is moving at a significant fraction of the speed of light. Neutron stars become observable as pulsars when their rotation and magnetic field combine to produce beams of electromagnetic radiation that sweep through space like the beam of a lighthouse. Neutron stars possess extraordinarily powerful magnetic fields, in many cases a trillion times stronger than Earth's magnetic field. These fields are not aligned with the rotation axis, so as the neutron star rotates, the magnetic poles sweep through space. Charged particles are accelerated along the magnetic field lines near the poles and emit intense beams of radiation, primarily in the radio part of the electromagnetic spectrum, though sometimes also in X-rays and gamma rays. When one of these beams sweeps across Earth with each rotation of the neutron star, radio telescopes detect a brief pulse of radiation. The pulses arrive with extraordinary regularity. The most stable pulses keep time more accurately than most atomic clocks, their pulses arriving at intervals that vary by less than a microsecond over years of observation. This remarkable regularity made pulsars scientifically useful almost immediately after their discovery in 1967 by Jocelyn Bell Burnell and Anthony Hewish. The first pulsar detected was initially nicknamed LGM1 for Little Green Men, because the regularity of the signal seemed almost too precise to be natural. It was soon recognized as a rotating neutron star, but the nickname reflects how startling its discovery was. Over time, pulsars slow down. The emission of radiation and the interaction of the pulsar's magnetic field with the surrounding environment carry energy and angular momentum away from the rotating neutron star. The rotation rate decreases gradually, and the pulsar's pulses become slightly less frequent over time. By measuring the rate at which a pulsar is slowing down, astronomers can estimate its age and the strength of its magnetic field. But not all pulsars are slowing down in isolation. Some pulsars exist in binary systems paired with a companion star. In these systems, material can flow from the companion star onto the neutron star, a process called accretion. The accreting material carries angular momentum with it, and as it falls onto the neutron star, it spins the neutron star up, reversing the usual trend of slowing rotation and pushing the pulsar to ever faster rotation rates. This spin-up process, operating over millions of years of steady accretion, is how millisecond pulsars are believed to form. They are old neutron stars that have been recycled by their companions, spun up to extraordinary rotation rates through the steady accumulation of angular momentum. Millisecond pulsars are sometimes called recycled pulsars for this reason. They represent a remarkable case of angular momentum being transferred from one object to another over an extended period, with the end result being some of the fastest rotating macroscopic objects in the known universe. The study of pulsars has yielded extraordinary scientific results beyond simply cataloging rotation rates. Binary pulsar systems have provided some of the most precise tests of general relativity ever performed. The first binary pulsar system, discovered in 1974 by Russell Hulse and Joseph Taylor, consists of two neutron stars orbiting each other. The system is slowly losing energy as it emits gravitational waves. ripples in spacetime predicted by Einstein's general theory of relativity. The rate at which the orbit is decaying matches the predictions of general relativity with remarkable precision, providing strong indirect evidence for gravitational waves decades before they were directly detected by the LIGO Observatory in 2015. Pulsars also serve as probes of interstellar space. As pulsar signals travel across the galaxy to reach our telescopes, they pass through clouds of electrons in the interstellar medium. Different frequencies of radio waves are slowed by slightly different amounts as they pass through this electron gas, causing the pulses to arrive at slightly different times at different frequencies, a phenomenon called dispersion. By measuring this dispersion, astronomers can estimate the density of electrons along the line of sight to the pulsar, mapping the structure of the interstellar medium across vast distances. Rotation, in the case of pulsars, has been transformed from a simple physical property into a scientific instrument of extraordinary precision. The spin of a neutron star encodes information about its birth, its history, its companion, and the space between it and us. Nowhere else in the universe does rotation carry so much information in such a compact and precisely measurable package. Chapter 8. Black Holes and Spin. Beyond neutron stars, at the extreme end of stellar death, lies a class of objects whose relationship with rotation is even more profound and more deeply connected to the fundamental structure of spacetime. Black holes are regions of spacetime where gravity has become so strong that nothing, not matter, not light, not any signal of any kind, can escape once it has crossed a boundary called the event horizon. They form when the collapsing core of a massive star is too heavy, even for neutron degeneracy pressure to halt, or through other processes such as the direct collapse of extremely massive gas clouds in the early universe, or the merger of two neutron stars. The simplest black holes, described by a solution to Einstein's equations called the Schwarzschild solution, have no rotation. They are perfectly spherical, characterized entirely by their mass. The event horizon of a non-rotating black hole is a perfect sphere, and the geometry of spacetime around it is symmetric in all directions. But simple black holes are almost certainly not what nature actually produces. Every object that collapses to form a black hole carries angular momentum. The original star was rotating. Angular momentum is conserved through the collapse. The resulting black hole must therefore also carry angular momentum. It must spin. Rotating black holes are described by a different solution to Einstein's equations, found in 1963 by the New Zealand mathematician Roy Kerr. These rotating black holes are called Kerr black holes, and their geometry is dramatically different from their non-rotating counterparts. A Kerr black hole is not spherically symmetric. Its rotation introduces a preferred direction, the axis of spin, and the geometry of spacetime around it reflects this asymmetry. The event horizon of a rotating black hole is no longer a perfect sphere, but is instead slightly flattened, bulging at the equator, and compressed at the poles in a way that mirrors the effect of rotation on ordinary objects. More significantly, the region of spacetime just outside the event horizon is profoundly altered by the black hole's spin. This altered region is called the ergosphere. The name comes from the Greek word for work, and it reflects a property of the ergosphere that has no parallel in everyday physics. Within the ergosphere, the rotation of the black hole is so powerful that spacetime itself is dragged along with it. An object within the ergosphere, even a beam of light attempting to travel in the opposite direction to the black hole's rotation, cannot remain stationary relative to distant observers. It is carried around by the dragging of spacetime, whether it chooses to be or not. This effect, the dragging of spacetime by a rotating mass, is called frame dragging, or more formally, the lens-Thirring effect. It is not unique to black holes. Any rotating mass drags spacetime around it to some degree. Earth's rotation drags spacetime in its vicinity by an extremely tiny but measurable amount, an effect that was confirmed by the Gravity Probe B experiment, a NASA satellite mission that measured the precession of gyroscopes in Earth orbit and detected the minuscule frame dragging produced by Earth's rotation. For black holes, frame dragging is not a tiny perturbation, but a dominant feature of the surrounding spacetime. The ergosphere lies outside the event horizon, which means objects can enter and exit it. This property opens a remarkable theoretical possibility first proposed by the physicist Roger Penrose in 1969. In what is now called the Penrose process, an object entering the ergosphere can in principle split into two pieces, with one piece falling into the black hole and the other escaping to infinity. Because of the geometry of the ergosphere, the escaping piece can carry away more energy than the original object brought in. The additional energy comes from the rotational energy of the black hole itself. The black hole loses a small amount of its spin in the process. Through repeated applications of this process, it would theoretically be possible to extract a significant fraction of the total energy stored in a rotating black hole spin. Up to about 29% of the black hole's total mass energy, which is an enormous quantity by any practical measure. Whether the Penrose process operates in nature in any significant way is not certain, but related mechanisms may play a role in some of the most energetic phenomena in the universe. The relativistic jets, narrow focused streams of plasma moving at close to the speed of light, that emerge from the cores of active galaxies and from some neutron star and black hole binary systems, may be powered in part by the rotational energy of spinning black holes, extracted through mechanisms related to the Penrose process and to the interaction of the black hole's rotation with surrounding magnetic fields. The spin of a black hole is characterized by a parameter astronomers call A, representing the angular momentum per unit mass of the black hole. This parameter ranges from 0 for a non-rotating black hole to a maximum value for a black hole spinning as fast as physically possible. A black hole at maximum spin is said to be an extremal Kerr black hole. At maximum spin, the event horizon shrinks to the minimum possible size and the ergosphere extends to its maximum extent. Whether any real black holes approach this extreme spin is unknown, though there are observational hints that some supermassive black holes in the centers of galaxies may have spin parameters close to the maximum. Measuring the spin of a black hole is a significant observational challenge. Unlike mass, which can be determined from the orbital dynamics of objects around the black hole, spin requires more subtle measurements. Two primary methods have been developed. The first uses the X-ray emission from hot gas in the accretion disk very close to the black hole. The innermost edge of the accretion disk depends on the black hole's spin. A faster spinning black hole allows stable orbits closer to the event horizon, and by measuring the spectrum of X-ray emission from this region, astronomers can estimate the spin. The second method uses a technique called ion line spectroscopy, examining the shape of the emission line from ion atoms in the inner accretion disk, which is distorted in characteristic ways by the strong gravity and rapid motion near the black hole. The 2019 image of the black hole at the center of the galaxy M87, produced by the Event Horizon Telescope collaboration, provided a visual representation of the shadow cast by the black hole's event horizon against the bright glow of the surrounding accretion disk. The asymmetry in the brightness of the ring in that image, one side appearing brighter than the other, is consistent with the effects of rotation and relativistic beaming, providing additional information about the black hole's spin and the orientation of its rotation axis relative to our line of sight. Rotation, for black holes, is not merely a property. It fundamentally alters the structure of space-time in the vicinity of the black hole, creates regions with no classical parallel, and stores energy that can, in principle, be extracted. The spin of a black hole is one of only 3 quantities needed to completely describe it, the others being its mass and its electric charge, though astrophysical black holes are expected to have negligible electric charge. Everything else about a black hole's history, what it was made of, what fell into it, what stars it consumed, is lost behind the event horizon. Only mass, charge, and spin remain as observable properties. This striking simplicity is sometimes called the no-hair theorem, a colorful way of saying that black holes carry no distinguishing features beyond these 3 numbers. In this sense, the spin of a black hole is one of its most fundamental characteristics. It is a memory of the angular momentum that existed before the black hole formed, preserved and concentrated into one of the simplest and most extreme objects the universe produces. Chapter 9. Accretion Disks. Throughout our journey so far, we have encountered accretion disks in several contexts. They appeared around the infant sun as the solar nebula flattened into a rotating disk of gas and dust. They appeared around neutron stars in binary systems, where infalling material spins up the neutron star to millisecond rotation rates. They appeared around black holes, glowing with X-ray emission from material heated to extreme temperatures as it spirals inward. In each case, the disk appeared naturally, without being imposed from outside. It emerged from the physics of rotating matter falling under gravity. This repeated appearance is not a coincidence. Accretion disks are one of the universe's most reliable structures, forming wherever matter with angular momentum falls toward a central gravitating body. Understanding why they form and how they behave gives us a window into one of the most fundamental consequences of rotation in astrophysics. The basic reason accretion disks form is straightforward and connects directly to everything we have covered about angular momentum conservation. When gas or dust or any collection of matter begins falling toward a central object, a forming star, a neutron star, a black hole, the infalling material almost always carries some angular momentum. It is not falling perfectly straight inward. It has some sideways motion, some rotation around the central body. As this material falls inward, its rotation rate increases, just as we have seen in every other context involving collapsing or concentrating matter. But there is a competing effect. The material cannot simply spiral freely inward without limit, because as it moves to smaller radii, the conservation of angular momentum demands that it move faster. At some radius, the centrifugal effect of this rotation balances gravity, and the material can no longer fall inward without first losing some of its angular momentum. This is the key point. To accrete, to actually fall all the way onto the central object, the infalling material must somehow get rid of angular momentum. It cannot simply carry it inward indefinitely. Angular momentum must be transferred outward through the disk, while mass flows inward. The mechanisms by which this transfer occurs are complex, involving turbulence, magnetic fields, and viscous interactions between adjacent layers of gas orbiting at slightly different speeds. The process begins when infalling material from different directions collides. These collisions are inelastic. They dissipate energy as heat. Kinetic energy is lost, but angular momentum is conserved. The result is that the random three-dimensional distribution of infalling material gradually settles into a single preferred plane. The plane defined by the net angular momentum vector of all the infalling material combined. Collisions between material above and below this plane cancel out the vertical components of motion, leaving material orbiting in a flattened configuration. This is why accretion disks are always flat. Not because something forces them into a flat shape from outside, but because the physics of collisions and angular momentum conservation naturally selects a single preferred orbital plane and damps out motion perpendicular to it. The disk is the lowest energy configuration for a given amount of angular momentum. Within the disk, material orbits the central object following approximately Keplerian orbits, the same elliptical orbital mechanics that govern planets around the Sun. Material at smaller radii orbits faster than material at larger radii. Adjacent rings of material in the disk therefore orbit at slightly different speeds, with inner rings moving faster than outer rings. This differential rotation creates friction between adjacent layers, a viscous interaction that transfers angular momentum from inner, faster-moving material outward to slower-moving material at larger radii. As achieves a result, material in the inner disk gradually loses angular momentum, moves to smaller orbits, and eventually accretes onto the central object. Material in the outer disk gains angular momentum and spreads outward. The energy released as material falls through the gravitational potential well of the central object is converted to heat through these viscous interactions. Accretion disks can be extraordinarily luminous as a result. In the case of a black hole with a well-developed accretion disk, the efficiency of energy conversion, the fraction of the infalling matter's rest mass energy that is radiated away before the material crosses the event horizon, can be significantly higher than the efficiency of nuclear fusion. Nuclear fusion converts less than 1% of mass to energy. Accretion onto a moderately spinning black hole can convert several percent of infalling mass to energy. Accretion onto a maximally spinning black hole can convert up to 42% of infalling mass to energy. An extraordinary figure that makes accreting black holes among the most efficient energy sources in the universe. This efficiency is the reason that active galactic nuclei, galaxies with actively accreting supermassive black holes at their centers, can outshine all the stars in their host galaxy combined. The luminosity comes not from nuclear burning, but from the conversion of gravitational potential energy to heat and radiation as matter spirals down through the accretion disk. Quasars, the most luminous of these active nuclei, shine with luminosities equivalent to trillions of suns, powered entirely by the accretion process and the angular momentum that keeps infalling matter temporarily in orbit, rather than falling straight through. The structure of an accretion disk around a stellar mass black hole or neutron star in a binary system is shaped by several temperature zones. In the innermost regions closest to the central object, temperatures reach millions of degrees and the disk emits primarily in X-rays. Moving outward, temperatures decrease and the emission shifts to ultraviolet, then optical, then infrared wavelengths. This temperature gradient across the disk means that different parts of the disk glow in different colors. And by analyzing the full spectrum of light from an accretion disk, astronomers can piece together the disk's structure and the mass and spin of the central object. In protoplanetary disks around young stars, the physics is similar in principle, but the scales and temperatures are very different. The disk around a young sun-like star is much cooler and much larger than the accretion disk around a compact object. The central temperature ranges from a few thousand degrees near the star to just tens of degrees in the cold outer regions. The material in the disk is a mixture of gas and solid particles, silicate dust, ice grains, and more complex organic molecules. The angular momentum transport in protoplanetary disks is thought to be driven partly by magnetic fields threading through the disk and partly by gravitational instabilities when the disk is sufficiently massive. Over millions of years, the solid particles in a protoplanetary disk grow from microscopic grains to pebbles, boulders, and eventually planetesimals through the accumulation process we discussed in Chapter 2. The disk is simultaneously the cradle of planetary formation and the reservoir of angular momentum that will be distributed among the planets, moons, and other bodies that emerge from it. By the time the disk has dissipated, cleared away by the radiation and stellar wind of the young star, the angular momentum it contained has been parceled out among all the objects that formed within it. Accretion disks also play a role in shaping the spin of the central objects they surround. A neutron star accreting from a disk is spun up, as we discussed in the previous chapter. A black hole accreting from a disk can also have its spin altered over time. Material spiraling inward from a prograde disk, one orbiting in the same direction as the black hole's spin, adds angular momentum aligned with the black hole's existing spin, increasing it. Material from a retrograde disk removes angular momentum and reduces the spin. Over the long lifetime of an actively accreting black hole, the cumulative effect of accretion on the black hole's spin can be significant. There is a further consequence of disk accretion around spinning black holes that connects to some of the most spectacular phenomena in observational astronomy. When the spin axis of a black hole is misaligned with the angular momentum axis of its accretion disk, the frame dragging effect we discussed in Chapter 8 causes the inner portion of the disk to precess, to wobble around the spin axis of the black hole. This effect, called the Bardeen-Peterson effect, tends to warp and align the inner disk with the black hole's equatorial plane, while the outer disk retains its original orientation. The result can be a twisted, warped disk with complex geometry. These warped disks can produce quasi-periodic oscillations in the X-ray emission from black hole binary systems, flickering patterns in the X-ray brightness that repeat on timescales of seconds to minutes, driven by the precession of the inner disk. Modeling these oscillations allows astronomers to probe the geometry of spacetime very close to the event horizon, providing some of the most direct observational tests of general relativistic effects around rotating black holes. Accretion disks are, in a very real sense, angular momentum made visible. They exist because matter has angular momentum and cannot surrender it instantly. They shine because the process of surrendering angular momentum releases energy. They flatten because angular momentum conservation selects a preferred plane. They connect the largest supermassive black holes in the centers of galaxies to the smallest protoplanetary disks around newly forming stars through the same underlying physics, the same insistence of angular momentum on being conserved, transferred, and slowly redistributed rather than simply disappearing. Chapter 10. Galaxies in Rotation. When we step back from individual stars and stellar remnants and consider the universe at the scale of galaxies, rotation remains one of the most prominent and defining features of what we observe. Spiral galaxies, the most visually striking category of galaxy, and the type to which our own Milky Way belongs, are defined by their rotation. Their sweeping arms, their flattened disks, their central bulges, and the distribution of stars and gas within them are all shaped by the dynamics of rotation operating over hundreds of millions to billions of years. A galaxy like the Milky Way is an enormous structure. It contains somewhere between 100 and 400 billion stars, along with vast quantities of gas, dust, and an even larger invisible component of dark matter that we will explore in the next chapter. The disk of the Milky Way spans roughly 100,000 light-years across. Our solar system sits about 26,000 light-years from the galactic center, well within the disk, orbiting the center of the galaxy at a speed of approximately 230 kilometers per second. At this speed, it takes our solar system roughly 225 to 250 million years to complete one full orbit around the galactic center, a period sometimes called a cosmic year or a galactic year. The rotation of a spiral galaxy is not like the rotation of a solid disk. Just as the Sun rotates differentially, with different latitudes completing rotations at different rates, a galaxy rotates in a complex way that varies with distance from the center. But the pattern of galactic differential rotation is different from the solar case and reflects the distribution of mass within the galaxy. For a simple system, where most of the mass is concentrated at the center, like the solar system, where the Sun contains nearly all the mass, the orbital speed of objects decreases with distance from the center following a predictable mathematical relationship. Objects close to the center move fast. Objects far from the center move slowly. This is the pattern described by Kepler's laws of planetary motion, and it is what we observe in our solar system. Mercury orbits the Sun much faster than Neptune does. For a galaxy, if most of the mass were concentrated in the central bulge, we would expect to see a similar pattern. Stars near the center would orbit quickly, and stars far out in the disk would orbit more slowly. When astronomers in the mid-20th century began measuring the rotation speeds of stars and gas clouds at different distances from the centers of spiral galaxies, they expected to find this pattern. What they found instead was profoundly unexpected and became one of the most important observational discoveries in modern astronomy. The rotation speed of stars and gas in spiral galaxies does not decrease with distance from the center, the way Kepler's laws would predict. Instead, it remains roughly constant, or in some galaxies even increases slightly, out to the very edges of the observable disk and beyond. These flat rotation curves, as they are called, indicate that the mass distribution in spiral galaxies is very different from what the visible matter alone would suggest. Vera Rubin and Kent Ford were among the first astronomers to systematically document flat rotation curves across a large sample of spiral galaxies in the 1970s, building on earlier work by several researchers including Fritz Zwicky, who had first proposed the existence of missing mass in galaxy clusters in the 1930s. Rubin and Ford's meticulous measurements of rotation curves in dozens of galaxies made the case for missing mass undeniable. The stars and gas we could see were simply not massive enough to produce the observed rotation speeds, particularly at large distances from the galactic center. Something else had to be there. That something else is what we now call dark matter, a form of matter that does not emit, absorb, or reflect light, and is therefore invisible to telescopes that detect electromagnetic radiation. Dark matter interacts with ordinary matter and with itself primarily through gravity. Its presence is inferred not from direct detection, but from its gravitational influence on the things we can see. We will explore dark matter in depth in the next chapter. For now, the key point is that the rotation of spiral galaxies told us, before we had any other evidence, that the universe contains far more matter than we can directly observe. The rotation curves of galaxies also tell us about the structure of dark matter in and around galaxies. The flat rotation curve extending to large radii implies that the mass distribution continues to grow as we move outward, well beyond the visible disk of stars. This has led to the model of galactic dark matter halos, vast, roughly spherical distributions of dark matter that surround and extend far beyond the visible galaxy. The visible disk of stars and gas that we see is embedded within this much larger dark matter halo, like a thin coin sitting at the center of an invisible sphere many times its diameter. Within the visible disk, the rotation of a spiral galaxy produces its most iconic feature, the spiral arms. These luminous structures, tracing arcs across the disk of a galaxy, are not permanent concentrations of the same stars moving together through space. If they were, the differential rotation of the galaxy would have wound them up into unrecognizable smears over billions of years, since the inner parts of the galaxy rotate faster than the outer parts. Instead, spiral arms are better understood as density waves, regions of slightly enhanced density that move through the disk as a wave pattern, independent of the motion of the individual stars. As stars and gas clouds orbit the galaxy and pass through a spiral arm, they are temporarily compressed by the slightly higher gravitational density of the arm. This compression can trigger the collapse of gas clouds into new stars, which is why spiral arms are often sites of active star formation, filled with bright young blue stars and glowing nebulae that light up the arm and make it visible. The arm itself persists as a wave pattern long after the individual stars that illuminated it have moved on. The Milky Way has two primary spiral arms, the Sagittarius arm and the Perseus arm, along with several shorter arm segments and spurs. Our solar system sits in one of these smaller features, the Orion spur, positioned between the major arms. Because we are embedded within the disk of the galaxy and cannot step outside it to view it from above, our knowledge of the Milky Way's spiral structure has been assembled painstakingly from observations of stellar positions, gas cloud velocities, and radio emission from hydrogen atoms across the disk. Elliptical galaxies, the other major category of large galaxy, rotate very differently from spirals, or in many cases barely rotate at all. Elliptical galaxies are three-dimensional, roughly egg-shaped systems supported against gravitational collapse, not primarily by rotation, but by the random motions of their stars. Stars in an elliptical galaxy orbit the center in all directions, with no strong preferred plane of rotation. This stands in contrast to spiral galaxies, where the disk and the ordered rotation within it are defining characteristics. The difference in rotation between spiral and elliptical galaxies reflects their different formation histories. Spiral galaxies are thought to form and grow relatively gradually, accreting gas from their surroundings in a way that maintains the angular momentum of the infalling material and builds up the rotating disk over time. Elliptical galaxies are thought to form in part through mergers of smaller galaxies, violent collisions that scramble the ordered rotation of the merging systems and redistribute their stars into the random orbits characteristic of ellipticals. Galaxy mergers are not rare events on cosmic timescales. Galaxies are embedded in dark matter halos that extend far beyond their visible stars, and when two halos overlap, gravitational interactions begin to pull the galaxies together. The merger process unfolds over hundreds of millions to billions of years, involving multiple close passes, tidal distortions, and eventually the coalescence of the two systems into a single larger galaxy. The Milky Way itself is on a collision course with the Andromeda Galaxy, our nearest large spiral neighbor, and the two are expected to merge in roughly 4 to 5 billion years. The result will likely be a large elliptical galaxy, as the ordered rotations of both spirals are scrambled by the violence of the merger. The rotation of galaxies, then, is not merely an aesthetic feature of the universe's most beautiful structures. It is a record of how galaxies formed, a probe of the invisible dark matter that dominates their mass, and a dynamic property that evolves over billions of years through accretion and mergers. Understanding galactic rotation has been one of the most productive areas of observational and theoretical astronomy over the past half-century, and it continues to yield new insights as telescopes improve and simulations grow more sophisticated. Chapter 11. The Dark Matter Connection. In the previous chapter, we arrived at one of the most significant conclusions in modern cosmology through the simple act of measuring how fast galaxies rotate. The stars and gas we can observe are insufficient to account for the rotation speeds we measure. Something invisible must make up the difference. That something, dark matter, is now understood to be the dominant form of matter in the universe, outweighing all the atoms, molecules, stars, and gas. We can directly observe by a factor of roughly 5 to 1. Dark matter does not interact with light. It emits no radiation. It absorbs no radiation. It reflects no radiation. Every form of electromagnetic observation, radio telescopes, optical telescopes, X-ray observatories, gamma-ray detectors, is blind to it. Our knowledge of dark matter comes entirely from its gravitational influence on the things we can see. In this sense, dark matter is known through its effects rather than through any direct detection, much the way the wind is known through the movement of leaves rather than through direct sight. The rotation curves of spiral galaxies were among the earliest and most compelling lines of evidence for dark matter, but they were far from the only ones. On larger scales, the motions of galaxies within galaxy clusters tell a similar story. Fritz Zwicky, observing the Coma Galaxy cluster in 1933, noted that the individual galaxies within the cluster were moving far too fast to remain gravitationally bound to each other if the only mass present were the mass of the visible galaxies. The cluster should have dispersed long ago. Something massive and invisible must be providing the additional gravitational glue that holds it together. Gravitational lensing provides another independent line of evidence. When light from a distant source passes close to a massive object, the curvature of space-time around that object bends the light path, acting like a lens. The degree of lensing depends on the mass of the intervening object. When astronomers measure the lensing produced by galaxy clusters, they consistently find that the mass inferred from the lensing is far greater than the mass of all the visible matter in the cluster. The excess mass matches well with what is needed to explain the cluster's dynamics. It is dark matter, the cosmic microwave background, the faint glow of radiation left over from the early universe, which we will discuss in more detail in a later chapter, also bears the imprint of dark matter. The small temperature fluctuations in the cosmic microwave background encode information about the distribution of matter in the early universe. The pattern of these fluctuations is sensitive to the ratio of ordinary matter to dark matter. The best measurements of the cosmic microwave background indicate that ordinary matter makes up roughly 5% of the universe's total energy content. Dark matter makes up about 27%, and the remaining 68% is in the form of dark energy, the mysterious component driving the accelerating expansion of the universe. What is dark matter made of? This remains one of the most important unanswered questions in physics and cosmology. Numerous candidates have been proposed over the decades. Weakly interacting massive particles, or WIMPs, were for many years considered the most promising candidates. These hypothetical particles would have masses in a range accessible to particle accelerators and would interact with ordinary matter through the weak nuclear force as well as gravity, making them potentially detectable in laboratory experiments. Despite extensive searches using underground detectors, particle colliders, and indirect astronomical observations, no confirmed detection of WIMPs has been made. Other candidates include axions, extremely light particles originally proposed to solve a different problem in particle physics, sterile neutrinos, primordial black holes formed in the early universe, and a variety of other exotic possibilities. Each candidate has different predicted properties and different detection signatures. The search continues on multiple fronts simultaneously, and the possibility remains that dark matter is composed of something not yet imagined in any current theoretical framework. What we can say with confidence is what dark matter does, even if we cannot yet say what it is. Dark matter forms the scaffolding of the universe on large scales. In the early universe, before stars and galaxies existed, quantum fluctuations in the density of dark matter, tiny variations from place to place in the amount of dark matter present, provided the seeds around which ordinary matter later gathered under gravity. Where dark matter was slightly denser, gravity was slightly stronger. Ordinary matter flowed toward these concentrations, eventually forming the first stars and galaxies within dark matter halos. The large-scale structure of the universe, the cosmic web of filaments, sheets, and voids that we observe when we map the distribution of galaxies across vast distances, reflects the distribution of dark matter. Galaxies and galaxy clusters preferentially form at the intersections of dark matter filaments, where the density of dark matter is highest and the gravitational attraction is strongest. The voids between these structures are regions where dark matter density is low and where galaxies are correspondingly rare. In this picture, the rotation of spiral galaxies is intimately connected to the structure of dark matter on cosmological scales. A spiral galaxy's rotation curve is shaped by the combined gravitational influence of its visible disk and its surrounding dark matter halo. The shape of the rotation curve, how the rotation speed varies with radius, encodes information about both the distribution of stars and gas in the disk and the distribution of dark matter in the halo. By carefully modeling rotation curves, astronomers can decompose the contributions of visible and dark matter and map the dark matter distribution around individual galaxies. This decomposition reveals that dark matter halos are not uniform spheres, but have a characteristic density profile, higher density near the center, decreasing toward the edges, described mathematically by profiles that have been refined through decades of computer simulations of galaxy formation. The density of dark matter at the center of these halos, whether it rises steeply to a point or levels off to a central plateau, is a subject of active research and debate, with implications for the nature of dark matter and the physics of galaxy formation. The connection between dark matter and galactic rotation extends to the shapes of galaxies themselves. The gravitational potential of the dark matter halo influences the stability of the rotating disk, affecting whether the disk can maintain its spiral structure or whether it becomes susceptible to the formation of a central bar, a linear concentration of stars extending across the center of the galaxy that replaces the compact central bulge. Barred spiral galaxies, including the Milky Way, which is thought to have a prominent central bar, may owe aspects of their structure to the particular properties of their dark matter halos. Rotation, in this context, serves as our primary window into a component of the universe that is otherwise entirely hidden from view. We measure the spin of galaxies and find that what we can see is only a fraction of what must be there. The universe is heavier than it looks, and it is the careful measurement of rotation curves that reveal this truth to us most clearly and most convincingly. Chapter 12. Galaxy Clusters and Larger Structures. Having explored rotation at the scale of individual galaxies, we can now ask a natural question. Does rotation persist at even larger scales? Do galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, rotate as a whole? And what about the largest structures in the observable universe, the filaments and sheets of the cosmic web that stretch across hundreds of millions of light years? Is there rotation at those scales too? Or does the universe eventually reach a size at which spinning gives way to something else entirely? The answer, as with so many questions in cosmology, is nuanced and still being actively worked out by researchers around the world. But the broad picture is becoming clearer, and it reveals something interesting about the nature of angular momentum at the very largest scales the universe presents to US galaxy clusters, are the largest gravitationally bound structures in the universe. They contain anywhere from a few dozen to several thousand individual galaxies, along with enormous quantities of hot gas, called the intracluster medium, that fills the space between the galaxies and glows brightly in X-ray wavelengths. The total mass of a large galaxy cluster can reach several thousand trillion times the mass of the Sun, making clusters the most massive discrete objects in the cosmos. Observations over the past few decades have found evidence that at least some galaxy clusters do possess a degree of coherent rotation. This is detected by measuring the velocities of individual member galaxies along the line of sight. Galaxies on one side of the cluster will be moving slightly toward us relative to the cluster's average motion, while galaxies on the other side will be moving slightly away if the cluster is rotating. The velocity differences are small compared to the random motions of individual galaxies within the cluster, making the detection of cluster rotation a subtle statistical exercise rather than a straightforward measurement. Several studies have found statistically significant rotation signals in samples of galaxy clusters, suggesting that coherent rotation at the cluster scale is real, rather than an artifact of measurement noise. The rotation is slow. Even the fastest rotating clusters complete perhaps one full rotation over a time comparable to the current age of the universe. But it is present. The angular momentum responsible for this rotation was acquired during the formation of the cluster through the same kinds of processes that give angular momentum to galaxies and smaller structures. Tidal torques, gravitational twists exerted by neighboring mass concentrations during the early universe, are thought to be the primary mechanism. The tidal torque theory of angular momentum acquisition is one of the central ideas in the study of structure formation. In the early universe, small fluctuations in the density of dark matter and ordinary matter were present everywhere, seeded by quantum processes during a very early period of rapid expansion called inflation. As these fluctuations grew under gravity, neighboring density concentrations exerted gravitational torques on each other. A collapsing region of the universe that was not perfectly symmetric, which all real regions were not, experienced differential gravitational pulls from the matter surrounding it. These differential pulls imparted angular momentum to the collapsing region, setting it spinning before it had even formed into a recognizable structure. The amount of angular momentum acquired through tidal torques depends on the shape of the collapsing region and the distribution of surrounding matter. Regions that were more elongated and that sat in more asymmetric environments gained more angular momentum. Regions that were more spherically symmetric and whose surroundings were more uniformly distributed acquired less. This variation in angular momentum acquisition contributes to the wide range of rotation rates and orientations we observe among galaxies and galaxy clusters today. On scales larger than galaxy clusters, the universe is organized into the cosmic web, a vast network of filaments, sheets, and nodes that spans the entire observable universe. The filaments are thread-like concentrations of dark matter and galaxies stretching across hundreds of millions of light years. The sheets are flattened surfaces where two filaments meet. The nodes, where multiple filaments intersect, are the sites of the largest galaxy clusters. Between these structures lie vast voids, regions of very low density that occupy most of the volume of the universe, but contain only a small fraction of its matter. Within the filaments of the cosmic web, there is evidence for coherent rotation at remarkably large scales. Several observational studies have reported finding that the spin axes of galaxies within cosmic filaments tend to be aligned with the filament's long axis, or in some cases perpendicular to it, depending on the mass of the galaxy and the scale of the filament. These alignments, sometimes called intrinsic alignments, suggest that the angular momentum of individual galaxies is not entirely random, but is influenced by the large-scale structure in which the galaxy is embedded. The physical mechanism behind these alignments is thought to be related to tidal torques operating during the formation of the filaments. As matter flowed along filaments toward the dense nodes where clusters form, the tidal forces associated with this large-scale flow imparted correlated angular momentum to the galaxies forming within the filament. Galaxies that formed in similar environments within the same filament therefore ended up with spin axes that are statistically related to each other and to the orientation of the filament. These alignments are not perfect. They represent a statistical tendency rather than a strict ordering. Any individual galaxy in a filament might have a spin axis pointing in almost any direction. But when large samples of galaxies in filaments are analyzed together, the statistical signal of alignment emerges from the noise. The universe is not randomly spinning at all scales. There are subtle but real correlations in the directions of angular momentum across distances of hundreds of millions of light years. Whether coherent rotation exists at the very largest scales, across the entire observable universe, is a question that has been examined but remains unresolved. Some researchers have searched for evidence of a preferred spin axis for the universe as a whole, looking for patterns in the distribution of galaxy spin directions across the sky. The results have been mixed. Some studies have reported hints of a preferred direction, while others find no statistically significant signal. The observational challenges are enormous. The effects expected are tiny. The systematic errors in measuring galaxy spin directions are significant, and the sample sizes required to detect a cosmological scale signal are only now becoming available with the latest generation of large galaxy surveys. The standard cosmological model predicts that the universe as a whole should have no net angular momentum, for a reason rooted in the very earliest moments after the Big Bang. If the universe began in an extremely uniform state, as the evidence from the cosmic microwave background strongly suggests, then there was no preferred direction and no large-scale rotation. The angular momentum we observe in galaxies, clusters, and filaments is all locally generated through tidal interactions, not inherited from some primordial cosmic spin. If future observations were to convincingly detect a net rotation of the universe as a whole, it would require a significant revision of our current understanding of cosmology and the initial conditions of the Big Bang. For now, the picture that emerges is one in which rotation is abundant and widespread at all scales up to and including galaxy clusters and cosmic filaments, but in which the universe at the very largest scales appears to be without a dominant preferred spin direction. Angular momentum is generated locally through gravitational interactions rather than inherited from a single primordial source. The universe spins everywhere, but not all in the same direction, and not all from the same origin. Chapter 13. The Early Universe and Primordial Spin. To understand how rotation came to be so widespread in the universe, we need to go back to the very beginning, not just to the formation of the first stars and galaxies, but to the earliest moments of the universe's existence, when the conditions that would eventually give rise to all the angular momentum we observe were first being established. The universe began approximately 13.8 billion years ago in an event we call the Big Bang, though the name is somewhat misleading, since it was not an explosion in the conventional sense and did not occur at a single point in space. It was instead a rapid expansion of space itself from an extremely hot, dense state, in which all the matter and energy in the observable universe was concentrated into a region far smaller than any scale we can directly observe today. In the very earliest moments, fractions of a second after the beginning, the universe was dominated by radiation and a quark-gluon plasma, a state of matter in which the fundamental building blocks of protons and neutrons were not yet bound together into composite particles. As the universe expanded and cooled, protons and neutrons formed, and within the first few minutes, nuclear fusion produced the first atomic nuclei, primarily hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, set the initial chemical composition of the universe. At this extremely early stage, the universe was extraordinarily uniform. Temperature and density varied from place to place by only tiny amounts, fluctuations of roughly 1 part in 100,000. These tiny variations were not the result of any large-scale rotation or any preferred direction. They were quantum fluctuations, inherent uncertainties in the distribution of energy that arose from the quantum mechanical nature of the physical processes operating at that early time. Before this era, and before the formation of atomic nuclei, cosmologists believed the universe underwent a period of extraordinarily rapid expansion called inflation. During inflation, the universe expanded by an enormous factor in an extremely short time, stretching any initial quantum fluctuations to cosmic scales and smoothing out any large-scale irregularities that might have been present at the very beginning. One of inflation's key predictions, and one of its greatest observational successes, is that the universe should be extremely uniform on large scales, with small fluctuations of a very specific statistical character. This prediction matches beautifully with what we observe in the cosmic microwave background. Inflation also has implications for any primordial rotation. If the universe had any large-scale spin before inflation began, the expansion during inflation would have diluted it to undetectable levels, spreading whatever angular momentum existed across a volume so vast that its local effects would be negligible. This is one reason why the standard cosmological model predicts no net rotation for the universe as a whole. Inflation effectively resets the large-scale angular momentum budget to zero, leaving only the local angular momentum that will later be generated through gravitational interactions as structures form. After inflation ended and the universe settled into its more gradual expansion, the small density fluctuations that inflation had stretched to cosmic scales began to grow under gravity. Regions that were slightly denser than average exerted slightly stronger gravitational pulls on their surroundings, drawing in more matter and becoming progressively denser over time. This process of gravitational instability, the tendency of small density enhancements to grow, is the engine that drove all subsequent structure formation in the universe. As these density fluctuations grew and the first structures began to collapse, angular momentum began to be generated through tidal torques, as we discussed in the previous chapter. The first objects to collapse were the smallest, small dark matter halos forming within the first few 100 million years after the Big Bang. As these small halos merged and accumulated, they built up larger halos, and the galaxies that formed within them inherited the angular momentum accumulated through the merger history and tidal torque history of their parent halos. The first stars in the universe, called population 3 stars by astronomers, formed within these early dark matter halos from gas that had never been processed through a previous generation of stars. This gas was composed almost entirely of hydrogen and helium, with essentially none of the heavier elements that later generations of stars would manufacture through nuclear fusion. The first stars are believed to have been extremely massive by the standards of stars today, perhaps hundreds of times the mass of the Sun, because the absence of heavy elements changed the cooling properties of the gas in ways that prevented it from fragmenting into smaller pieces before collapsing. These first stars lived fast and died young. Their short lifetimes, perhaps 1 million years or less, compared to the 10 billion year lifetime of a Sun-like star, ended in supernovae or direct collapses to black holes. Their deaths seeded the surrounding gas with heavy elements for the first time, enriching the material from which subsequent generations of stars would form and changing the character of star formation in the universe permanently. The black holes left behind by the deaths of the most massive first stars are thought to be the seeds of the supermassive black holes that now reside at the centers of nearly all large galaxies. How these seed black holes grew to their current masses, some of them billions of times the mass of the Sun, in the available cosmic time is one of the most active areas of research in observational and theoretical cosmology. Accretion and mergers both play roles, and the spin of these growing black holes reflects their entire accretion and merger history in a way that we are only beginning to be able to probe observationally. The early universe, then, was not a spinning place in any global sense. It was a nearly uniform, nearly isotropic sea of matter and radiation, within which tiny fluctuations grew under gravity into progressively larger structures. Angular momentum was not present at the beginning in any cosmologically significant way. It emerged from the gravitational interactions of structures as they formed, grew, and merged. Every spinning galaxy, every rotating cluster, every aligned filament in the cosmic web represents angular momentum that was generated locally after the Big Bang, not inherited from any primordial cosmic rotation. This origin of angular momentum through structure formation, rather than primordial spin, is one of the more subtle but important features of our cosmological model. It means that the rotation we observe throughout the universe is a product of the universe's history, a record of gravitational interactions, mergers, and tidal torques accumulated over 13 billion years of cosmic evolution. The universe spins not because it began spinning, but because gravity is asymmetric, and asymmetric gravity generates angular momentum wherever matter is unevenly distributed. Chapter 14. Conservation of angular momentum. We have encountered angular momentum conservation in nearly every chapter of this exploration. It appeared when the solar nebula collapsed and spun faster as it contracted. It appeared when a figure skater pulled in their arms and accelerated their spin. It appeared when a massive star collapsed to form a neutron star spinning hundreds of times per second. It appeared when matter spiraling toward a black hole settled into a flat accretion disk, rather than falling straight through. In each case, the same principle applied. Angular momentum is conserved. It does not vanish. It does not simply dissipate into nothing. It persists, is transferred, and shapes the structures that emerge from physical processes across every scale we have examined. It is worth pausing here to give this principle the deeper attention it deserves. Conservation of angular momentum is not simply a rule that physicists have observed to hold true in many situations. It is a consequence of something more fundamental, a deep connection between the symmetries of nature and the quantities that physics conserves. Understanding this connection enriches our appreciation of why angular momentum conservation is so universal and so reliable. In the early 20th century, the mathematician Emmy Noether proved a theorem that has since become one of the most important results in theoretical physics. Noether's theorem states that every continuous symmetry of a physical system corresponds to a conserved quantity, the symmetry of a system under translation in time, the fact that the laws of physics are the same today as they were yesterday and will be tomorrow, corresponds to the conservation of energy, the symmetry under translation in space, the fact that the laws of physics are the same here as they are on the other side of the galaxy, corresponds to the conservation of linear momentum, and the symmetry under rotation, the fact that the laws of physics are the same regardless of which direction you are facing, corresponds to the conservation of angular momentum. This last symmetry is called rotational symmetry, or isotropy. The laws of physics do not have a preferred direction. There is no special axis built into the universe around which rotation is fundamentally different from rotation around any other axis. Physics works the same regardless of orientation. And because of this directional uniformity, angular momentum must be conserved. The conservation law is not an independent fact about the universe. It is a consequence of the universe's rotational symmetry, derived mathematically through Noether's theorem. This perspective reframes our understanding of why everything in the universe spins. It is not merely that spinning things tend to keep spinning because of inertia, though that is true. It is that the conservation of angular momentum is guaranteed by the isotropy of space itself. As long as space has no preferred direction, as long as the laws of physics are the same in all orientations, angular momentum will be conserved. The universe spins not because spinning is special, but because the universe is symmetric. Angular momentum conservation operates across an extraordinary range of scales and contexts. At the subatomic level, it governs the quantum mechanical spin of particles and the angular momentum of electrons in their atomic orbitals. At the human scale, it governs the motion of spinning tops, gyroscopes, boomerangs, and thrown balls. At the planetary scale, it governs the rotation of planets and the orbits of moons. At the stellar scale, it governs the spin-up of neutron stars and the formation of accretion disks. At the galactic scale, it governs the rotation of spiral galaxies and the tidal torquing of dark matter halos. At the cosmological scale, it governs the acquisition of angular momentum by galaxy clusters and cosmic filaments. In each of these contexts, the underlying principle is the same. Systems conserve their angular momentum in the absence of external torques. When angular momentum is transferred from one part of a system to another, the total remains constant. The universe keeps careful accounts of its rotation, and those accounts always balance. One of the most elegant demonstrations of angular momentum conservation involves gyroscopes. A spinning gyroscope resists changes to its orientation with a force that seems almost mysterious until you understand the underlying physics. When you try to tilt a spinning gyroscope, rather than simply tilting in the direction you push, it moves sideways. It precesses around an axis perpendicular to both the spin axis and the direction of the applied force. This behavior, called gyroscopic precession, is a direct consequence of angular momentum conservation. The angular momentum vector of the gyroscope resists being redirected, and the applied force causes it to precess rather than simply flip. Gyroscopic effects have practical applications that span from navigation to spacecraft attitude control. Before the era of electronic navigation systems, gyroscopes were essential components of inertial navigation systems used in aircraft and ships. A gyroscope, once set spinning and oriented in a known direction, maintains its orientation in space regardless of how the vehicle around it maneuvers. By measuring how much the vehicle has rotated relative to the gyroscope's fixed orientation, the navigation system can track the vehicle's attitude and heading without any external reference. The same principle, scaled up and refined, is used in the attitude control systems of spacecraft, where gyroscopic reaction wheels allow a spacecraft to rotate without any fuel expenditure by transferring angular momentum between the spacecraft body and the spinning wheels. The Earth itself behaves as a giant gyroscope in some respects. Its rotation axis maintains a roughly fixed orientation in space over short time scales, which is why the North Pole always points toward Polaris, the North Star. Over longer time scales, gravitational torques from the Moon and Sun cause Earth's rotation axis to precess slowly, tracing a cone in space over a period of approximately 26,000 years. This precession, known as the precession of the equinoxes, means that the celestial pole, the point in the sky that Earth's rotation axis points toward, traces a slow circle over millennia. Polaris is our current pole star, but 12,000 years ago the pole was near the star Vega, and in 12,000 years it will be near Vega again, as the precession cycle continues. Angular momentum conservation also plays a central role in some of the most dramatic events in astrophysics. When two neutron stars or two black holes spiral together and merge, a process that produces the gravitational wave signals detected by LIGO and Virgo, the final merged object must have angular momentum equal to the total angular momentum of the two merging objects, minus whatever angular momentum was radiated away in gravitational waves. The spin of the final merged black hole is therefore a direct consequence of the angular momenta of the two merging objects and the dynamics of the merger process. Measuring the spins of merged black holes through gravitational wave observations provides information about the masses and spins of the merging objects and about the physics of the merger itself. In the context of gravitational wave astronomy, angular momentum conservation has become a precision scientific tool. The waveform of a gravitational wave signal, the detailed pattern of how the gravitational wave's amplitude and frequency change over time as the two objects spiral together and merge, encodes detailed information about the masses, spins, and orbital configuration of the merging system. By comparing observed waveforms with theoretical predictions calculated from general relativity, astronomers can extract the angular momenta of the merging objects with remarkable precision. The conservation of angular momentum is, in a very deep sense, one of the universe's most fundamental commitments. It holds at every scale, in every context, across all of cosmic history. It is guaranteed not by any specific property of matter or energy, but by the isotropy of space itself, the fact that the universe has no preferred direction. As long as space remains isotropic, angular momentum will be conserved. The universe's rotation is not an accident or a coincidence. It is a mathematical necessity, written into the symmetry of space and enforced by one of the most beautiful theorems in all of physics. Chapter 15. Rotation and the Arrow of Time. Among the deeper questions that rotation raises, one of the most philosophically rich concerns its relationship to time. We experience time as having a direction, a flow from past to future that feels fundamental and inescapable. The past is fixed and inaccessible. The future is open and undetermined. This asymmetry between past and future is so deeply embedded in our experience of reality that it can seem like the most obvious feature of existence. Yet when physicists examine the fundamental laws of physics, they find something surprising. Most of those laws are symmetric with respect to time. They work equally well whether time flows forward or backward. The asymmetry of time, what physicists call the arrow of time, is not obviously present in the fundamental equations. Rotation enters this picture in several interesting ways. Consider a spinning planet viewed from space. If you were shown a recording of the planet spinning and asked whether the recording was playing forward or backward, could you tell? In the absence of other information, without watching anything fall, without seeing any heat flow, without observing any process of change other than the pure rotation itself, you could not. A planet spinning clockwise and a planet spinning counterclockwise are both perfectly valid solutions to the equations of gravitational and rotational dynamics. Nothing in those equations prefers one direction over the other. The rotation itself is time-symmetric. This time symmetry of pure rotation is a reflection of what we discussed in the previous chapter. Angular momentum conservation follows from rotational symmetry, the isotropy of space. And rotational symmetry is equally valid whether time runs forward or backward. The conservation of angular momentum does not distinguish between past and future. But the universe around us is not composed of pure rotation in isolation. It is composed of rotating objects that also radiate energy, transfer heat, undergo chemical and nuclear reactions, and interact with their environments in countless ways that are not time-symmetric. A neutron star spinning in space gradually slows as it radiates electromagnetic energy and angular momentum into its surroundings. Played backward, this would show a neutron star gradually spinning up without any apparent source of energy, a process that does not occur naturally and would immediately strike any physicist as playing in the wrong direction. The time asymmetry appears not in the rotation itself, but in the dissipative processes that accompany it. The source of the universe's arrow of time is generally understood to be thermodynamic in nature, rooted in the second law of thermodynamics. The second law states that the entropy of a closed system, a measure of the disorder or the number of possible microscopic configurations of the system, tends to increase over time. Systems evolve from ordered, low entropy states toward disordered, high entropy states. Heat flows from hot objects to cold objects, not the reverse. Gas expands to fill available volume rather than spontaneously concentrating in one corner. Ordered structures dissolve into disorder rather than spontaneously assembling from it. Rotation connects to this thermodynamic picture in subtle ways. A perfectly rotating rigid body, spinning without any internal friction or dissipation, has a fixed entropy and a conserved angular momentum and represents a time-symmetric system. Real rotating objects, however, are never perfectly rigid and frictionless. Tidal forces flex and heat them. Internal friction dissipates energy. Electromagnetic radiation carries energy and angular momentum away. All of these processes increase entropy and mark the direction of time. The early universe was in an extraordinarily low entropy state, highly ordered, nearly uniform, and far from the maximum entropy configuration that a collection of matter and energy of that total size could in principle occupy. The universe has been evolving toward higher entropy ever since, and this evolution is what defines the direction of time. The rotation we observe in the universe, in planets, stars, galaxies, and clusters, emerged as entropy increased and structures formed. Rotation is, in this sense, a product of the arrow of time rather than its cause. It arose as the low-entropy early universe evolved toward greater complexity and higher entropy through gravitational structure formation. There is a further connection between rotation and time in the context of general relativity. Rotating masses drag space-time around them, as we explored in the discussion of Kerr black holes and the lens-Thirring effect. In extreme cases, near maximally rotating black holes. This dragging of space-time is so severe that it affects the causal structure of the region, influencing which events can causally precede or follow which other events. The ergosphere of a rotating black hole is a region where the dragging of space-time has changed the relationship between space and time in fundamental ways, where the direction once called spatial has taken on some of the character of the temporal direction. These effects do not create time travel or allow the past to be revisited, but they do illustrate how deeply rotation, at the extremes of gravitational physics, is intertwined with the structure of space-time and the nature of time itself. Rotation is not merely a property of objects moving through time. In the strongest gravitational fields, it participates in shaping what time means and how it flows in the surrounding region of space-time. For most practical purposes, for planets, stars, and galaxies, the connection between rotation and time is less exotic but still present. The rotation of Earth defines our day. The orbital period of Earth around the Sun defines our year. The great cosmic rotation of the solar system around the center of the Milky Way defines the cosmic year of approximately 225 million Earth years. Rotation at every scale provides a clock, a way of measuring the passage of time by counting the cycles of a spinning system. In this sense, rotation and time are inseparable, not just philosophically, but practically. We have always measured time by counting rotations, from the ancient observation of day and night to the atomic clocks of modern physics, which count the oscillations of atoms, oscillations that are themselves a form of quantum mechanical rotation. Time and rotation are woven together throughout the universe. The arrow of time points in the direction of increasing entropy. Rotation is conserved along that arrow, persisting through all the changes entropy drives, outlasting the structures that produced it, and being redistributed rather than destroyed as systems evolve. In the very long run, when entropy has reached its maximum and the universe has settled into its final equilibrium, rotation will have been redistributed as broadly as possible, conserved in total but spread so diffusely that no individual spinning structure remains. That final state is far in the future. Until then, the universe continues to spin. Chapter 16. Spin in Quantum Mechanics, Everything we have explored so far has concerned rotation in the classical sense. Objects turning, orbiting, spinning on axes that can be pointed in any direction and measured with ordinary instruments. When we descend to the scale of fundamental particles, rotation appears again, but in a form so different from classical rotation that the word spin, while still used, carries an entirely different meaning. Quantum mechanical spin is an intrinsic property of fundamental particles. Electrons, protons, neutrons, photons, and quarks all possess spin. It is not the result of the particle physically rotating about an internal axis, the way a planet rotates about its geographic poles. Particles like electrons are treated in quantum mechanics as point-like objects with no spatial extent, and a point cannot rotate in the classical sense. Yet electrons carry angular momentum as surely as any spinning top, and that angular momentum is real, measurable, and consequential. Quantum spin comes in discrete units. The fundamental unit is a quantity related to Planck's constant, the same constant that governs the graininess of energy in quantum mechanics. Particles are classified by their spin value. Electrons, protons, and neutrons have spin 1/2, meaning they carry half a unit of the fundamental quantum of angular momentum. Photons have spin 1. The Higgs boson has spin 0. The graviton, if it exists as a quantum particle, is predicted to have spin 2. These spin values are not variable properties that can take any value. They are fixed characteristics of each particle type, as fundamental as the particle's mass or electric charge. Spin 1/2 particles have a particularly counterintuitive property. If you rotate one by 360 degrees, one full rotation, it does not return to its original quantum state. It requires a rotation of 720 degrees, 2 full rotations, to return to the original state. This has no classical analogue whatsoever. No macroscopic object behaves this way. It is a purely quantum mechanical phenomenon that reflects the deep mathematical structure of quantum spin, which is described by mathematical objects called spinors, rather than ordinary vectors. The consequences of quantum spin are pervasive and profound. The Pauli exclusion principle, the rule that no two identical fermions can occupy the same quantum state simultaneously, is a direct consequence of the half-integer spin of particles like electrons. It is this principle that determines the structure of atoms, preventing all electrons from crowding into the lowest energy orbital, and instead forcing them to occupy successively higher energy levels. Without the exclusion principle, chemistry as we know it would not exist. Atoms would all behave like hydrogen. No complex molecules would form. No life would arise. Quantum spin also underlies the phenomenon of magnetism. An electron's spin gives it a magnetic moment. It behaves like a tiny bar magnet. In many materials, these tiny magnetic moments cancel out, leaving no net magnetism. But in ferromagnetic materials like iron, quantum mechanical interactions cause the spins of neighboring electrons to align preferentially in the same direction, producing a macroscopic magnetic field. The magnetism of the compass needle, the data storage capacity of a hard drive, and the function of the electric motors that power modern technology all trace back to the quantum spin of electrons. Quantum spin is conserved in particle interactions, just as classical angular momentum is conserved in macroscopic interactions. When particles collide, decay, or are created, the total spin angular momentum of the system is preserved. This conservation law governs the outcomes of particle physics experiments and constrains which decay products are possible from which parent particles. The conservation of spin is one of the bookkeeping rules that every process in particle physics must obey. The connection between quantum spin and classical angular momentum is not merely metaphorical. At large scales, the quantum mechanical spins of many particles combine to produce the macroscopic angular momentum of bulk matter. The spin angular momentum of the electrons and nuclei in a rotating object contributes to the object's total angular momentum, alongside the orbital angular momentum of the electrons around nuclei, and the bulk rotational angular momentum of the object as a whole. In most macroscopic contexts, the quantum contributions are negligible compared to the bulk rotation, but they are there, and they are part of the same conserved total. Chapter 17. The Coriolis Effect. Returning from the quantum world to the surface of our own planet, we find rotation expressing itself in one of the most practically significant ways in all of Earth science. The Coriolis effect is the influence of Earth's rotation on the motion of objects moving across its surface or through its atmosphere and oceans. It is not a force in the conventional sense. It does not arise from any physical interaction between objects. It is instead a consequence of observing motion from within a rotating reference frame. To understand the Coriolis effect, consider standing at Earth's equator and throwing a ball northward toward the North Pole. At the equator, you and the ball are both moving eastward with Earth's rotation at a speed of roughly 1,600 kilometers per hour. As the ball travels northward, it maintains this eastward velocity because angular momentum is conserved and nothing is pushing the ball sideways. But the ground beneath the ball's path is rotating more slowly as the ball moves toward higher latitudes, because points closer to the poles travel smaller circles in the same 24-hour period and therefore move eastward more slowly. The ball, still carrying its original equatorial eastward velocity, moves eastward faster than the ground beneath it. From the perspective of an observer on the rotating Earth, the ball appears to curve to the right. This rightward deflection in the northern hemisphere and leftward deflection in the southern hemisphere is the Coriolis effect. Its magnitude depends on the speed of the moving object, its latitude, and Earth's rotation rate. It is negligible for small, slow-moving objects over short distances, which is why it does not noticeably affect the water draining from a bathtub, despite the popular belief that it does. It becomes significant for fast-moving objects covering large distances, weather systems, ocean currents, artillery shells over long ranges, and aircraft on extended flights. In the atmosphere, the Coriolis effect is one of the primary factors shaping the large-scale circulation patterns that determine global weather. Air flowing away from high-pressure regions or toward low-pressure regions is deflected by the Coriolis effect, causing it to curve rather than flowing directly from high to low pressure. The result is that large weather systems rotate. In the northern hemisphere, low-pressure systems, cyclones, rotate counterclockwise, with air spiraling inward and upward. High-pressure systems, anticyclones, rotate clockwise. In the southern hemisphere, these directions are reversed. Hurricanes, typhoons, and cyclones, whatever name they are given depending on their ocean of origin, all rotate in directions determined by their hemisphere. The Coriolis effect also drives the large-scale circulation of Earth's oceans. Ocean currents are deflected by the same mechanism that deflects atmospheric winds, producing the Great Gyres, rotating systems of ocean currents that circulate in each of the major ocean basins. In the North Atlantic, the gyre circulates clockwise, carrying warm tropical water northward along the American coast as the Gulf Stream before returning cold water southward along the European coast. These ocean gyres play a significant role in redistributing heat around the planet, moderating the climates of coastal regions and influencing the distribution of marine life. The Coriolis Effect is, in essence, angular momentum conservation made visible at the planetary scale. Moving air and water carry angular momentum acquired from Earth's rotation. As they move to different latitudes, conservation of angular momentum causes their rotation rate relative to the local surface to change, producing the apparent deflections we observe. Earth's rotation is not merely an astronomical curiosity. It is an active participant in shaping the atmosphere and oceans that make our planet habitable. Chapter 18. Rotation and Life on Earth. The rotation of Earth is so fundamental to life on this planet that it is easy to overlook how many of life's most basic conditions depend directly on it. Day and night, seasons, tides, climate patterns, the magnetic field, all are shaped in whole or in part by Earth's spin, and all are intimately connected to the conditions that allowed life to emerge and persist here over billions of years. The most immediate consequence of Earth's rotation is the cycle of day and night. The 24-hour rotation period divides each day into periods of illumination and darkness, driving the biological rhythms of nearly every living organism on Earth. Circadian rhythms, the internal biological clocks that regulate sleep, metabolism, hormone production, and countless other physiological processes, are tuned to Earth's rotation period. These rhythms are so deeply embedded in the biology of living things that they persist even in the absence of external light cues, maintained by internal molecular mechanisms that have evolved over billions of years of life on a rotating planet. The length of Earth's day has not always been 24 hours. In the distant past, Earth rotated significantly faster. 4 billion years ago, a day may have lasted only 6 to 8 hours. The Moon's tidal influence has gradually slowed Earth's rotation over geological time, lengthening the day by a small but measurable amount each century. The biological clocks of early life evolved in the context of much shorter days, and over billions of years of evolution, as days grew longer, life's rhythms adjusted accordingly. Earth's axial tilt of 23.5 degrees, itself a legacy of the ancient giant impact that formed the Moon, gives rise to the seasons. As Earth orbits the Sun, different hemispheres are tilted toward or away from it at different points in the orbit, producing the familiar cycle of summer and winter. The seasons drive the annual patterns of temperature, precipitation, and daylight that structure ecosystems around the world. They drive the migrations of animals, the flowering of plants, the breeding cycles of countless species. Life on Earth is profoundly organized around the annual rhythm, produced by the combination of Earth's orbital motion and the tilt of its rotation axis. Earth's rotation also plays an indirect but crucial role in maintaining the magnetic field that protects life from harmful cosmic radiation. Earth's magnetic field is generated by the motion of liquid iron in the outer core, a process called the geodynamo. The rotation of Earth influences the pattern of convection in the outer core, organizing the flow of conducting fluid in ways that sustain the magnetic field through a self-reinforcing dynamo process. Without Earth's rotation, the geodynamo would operate differently, or might not sustain a stable magnetic field at all. The magnetic field deflects the solar wind, the stream of charged particles flowing outward from the Sun, protecting Earth's atmosphere from being gradually stripped away over geological time. Mars, which lost most of its global magnetic field billions of years ago, has also lost most of its atmosphere to the solar wind, leaving it with a thin, cold, largely inhospitable surface environment. Earth's rotation, by helping sustain the geodynamo, has been one of the factors preserving the atmospheric conditions that make complex life possible. The Moon's stabilizing influence on Earth's axial tilt, preventing the dramatic polar wander that Mars experiences, is itself a consequence of the angular momentum exchange between Earth and Moon that we discussed in the chapter on tidal locking. Earth's rotation and the Moon's orbit are linked through angular momentum in a way that has provided billions of years of relative climatic stability, a stability that may have been important for the long, slow process of biological evolution that eventually produced complex multicellular life. Rotation, then, is not merely a backdrop to the story of life on Earth. It is woven into the conditions that made life possible, the rhythms that organize biological processes, and the planetary systems that have maintained habitability over geological time. The universe's tendency to spin has, on at least one planet that we know of, contributed to the emergence of creatures capable of looking up at the spinning sky and asking why everything turns. Closing. We have traveled a long way tonight, from the abstract foundations of angular momentum and Noether's theorem, through the formation of the solar system and the varied rotations of planets and moons, out to spinning stars and pulsars, and the frame dragging space-time around rotating black holes. We have seen accretion disks forming wherever angular momentum prevents matter from falling freely inward. We have watched spiral galaxies reveal invisible dark matter through the simple act of spinning. We have traced angular momentum through galaxy clusters and cosmic filaments, back to the early universe where none of it yet existed, and forward through structure formation to the rich, rotating cosmos we inhabit today. What emerges from all of this is a picture of the universe as a place where angular momentum is one of the most enduring and pervasive quantities there is. It cannot be created from nothing. It cannot disappear into nothing. It moves through systems, concentrates in collapsing structures, spreads through interactions, and persists across timescales that dwarf the entire history of life on Earth. The spinning of a galaxy and the spin of an electron are separated by 60 orders of magnitude in scale, yet both are expressions of the same conserved quantity, both guaranteed by the same underlying symmetry of space. There is something quietly reassuring about this. In a universe of constant change, of stars being born and dying, galaxies colliding and merging, matter and energy flowing and transforming, rotation endures. The angular momentum present in a collapsing cloud of gas billions of years ago still exists today, distributed among the planets and moons and asteroid families that inherited it. The spin imparted to a neutron star in a catastrophic explosion persists for millions of years, slowing only gradually as the pulsar radiates into the surrounding space. The rotation of a spiral galaxy, shaped by dark matter and tidal torques over billions of years, continues turning long after the individual stars that trace its arms have lived and died. The universe spins because it cannot help but spin, because angular momentum is conserved, because space is symmetric, because the laws of physics are the same in every direction. From the moment the first structures formed from the smooth early universe, gravity began generating angular momentum in every collapsing cloud, every merging halo, every infalling stream of gas. That angular momentum has been accumulating and redistributing ever since, filling the cosmos with spinning objects at every scale. As you rest here, the Earth beneath you is turning at roughly 1,600 kilometers per hour at the equator. The solar system is sweeping around the galactic center at 230 kilometers per second. The Milky Way itself is moving through the local universe part of structures that are themselves in motion. All of this rotation is happening continuously, quietly, without effort or interruption. You do not feel it. The motion is too smooth, too constant, too vast, but it is there, an unbroken thread of angular momentum connecting the ground beneath you to the early universe, connecting the rhythm of day and night to the conservation law that governs the spin of black holes, connecting the turning of seasons to the same symmetry of space that keeps pulsars keeping perfect time across thousands of light years. Everything spins. Everything has always spun. And in the quiet of this night, in whatever stillness you have found, the universe continues turning around you, patient, silent, and persistent as the laws that keep it turning.